Good afternoon. Thank you very much for being here. This is joint work with Edgar from Siegen University. I'm going to talk about the history of computer science from, let's say, 1960 till the present. And I'm going to engage a little bit with Wittgenstein. My talk consists of three parts. Number one is basically addressing the question, what is computer science? In the second part, I'm going to refine the question. And then in the third part, I'm going to present one answer based on our research, which is that computer science is based on a conflation. Here are all the subsections. There's no point going through this because this slide will recur over and over again as I go through my presentation. But to start off with, I'm going to introduce the concept of a Turing machine very briefly, and then try to, in socio-technical terms, argue that the Turing machine is a boundary object. And if I succeed in that, then in the third point here, I'm going to try to argue that the Turing machine is not a boundary object. Okay, so just one slide. Everybody is acquainted with some of the writings of Alan Turing, especially this 1936 article on computable numbers. This is a picture of a Turing machine from the mid-1950s from Kemeny, a former PhD student of Alonzo Church. And as I said, I'm going to skip the epistemological transformations from Turing's 1936 article on automatic machines to the first textbook definitions in the 1950s. Instead, I'm going to talk about all these textbooks from, let's say, around 1960 till the present. And every textbook has a slightly different definition compared to the definitions in the other textbooks, more or less. I mean, this is just, we can go through the books and I can show you. So this is just a check for the notion of Turing machine, but based on all of those textbooks, I will now try to argue that the Turing machine is a boundary object. To do that, I'm going to engage with Susan Leigh Starr and her co-author. These are seminal papers on boundary objects. I'm going to have to argue that there's plasticity involved when we go through all those textbooks. We have robustness and we have interpretive flexibility. So let's start with the first item. A synonym is mathematical variability. If we go through all these textbooks, well, some textbooks will define a Turing machine with a 2 infinite tape. Other textbooks will define a Turing machine with a 1 infinite tape. Yet other textbooks will not rely on 1 tape, but let's say on 3 tapes, like we have an input tape, a work tape, and an output tape. All of this does not matter in terms of computability, so this is all just in order. And a third example of mathematical variability is the kind of symbols that can be written on a Turing tape. Unary notation is one example, binary notation, or here we have 3 kinds of symbols, a 0, a 1, and a B for blank. This is all just fine. So plasticity is something we can check off based on going on an analysis of all these textbooks. What about robustness? Is there some immutable content in each of these textbooks? Yes, there is. Each textbook definition adheres to what I call the neo-Russellian tenet after Bertrand Russell. And every textbook says something like this, postulated. Everything a computer or a physical object in general can do, a Turing machine can do as well. For example, in Scott Aronson's book in 2013, he says, the human brain is nothing other than a hot, wet Turing machine. And in a book that I read as a student in computer science 22 years ago, I had to accept this statement. A Turing machine can do everything a real computer can do. And you can already be a little bit philosophical about the first two and the second do. Clearly, we're talking about different categorical realms and so on and so forth. But fine. I'm not going to be too philosophical at this point in my talk. This is an historical observation that in all these textbooks, there is this stronger form of logicism, a computational form of logicism in play. That's why I say neo-Russellian. And I'm going to have another slide on this. The neo-Russellian tenet has enabled computer scientists to manage an incessant evolution of computing paradigms ranging from asynchronous and interactive computing to quantum computing. All these computations fit under the umbrella of the universal Turing machine. And defending this claim, this universality claim, is a conditio sine qua non to being called a computer scientist. And if you are a computer scientist and you start to question the claim, and there are people like this in the history as well, like Giuseppe Longo is one person, Carl Hewitt is another example. If you start to question the claim, you're moved to the fringes of computer science. So the neo-Russellian tenet is, I want to stress this, a proclaimed isomorphism between processes running in logical space, Turing machines in particular, and processes, causal processes running on your laptops, your iPhones, and so on. Okay, so the third component to convey to you that the Turing machine is a boundary object is interpretive flexibility. Well, indeed, if we look at these historical writings, there are different receptions of the unsolvability of the halting problem of Turing machines. We can look at Martin Minsky in the US and his contemporary Edgar Dijkstra in the Netherlands around 1970. They were both writing about the unsolvability of the halting problem and trying to understand what does this actually mean for us in the context of computer programming, because these were not magicians. Alright, the unsolvability of the halting problem, and I'm paraphrasing, was an obstruction for the computation scientist according to Minsky, because he was, for him, the American scientist domineers the engineer, and so the word engineer in the US has less prestige than the word scientist, and today in large parts in Europe this is also the case. But for Dijkstra, around 1970, he interpreted the unsolvability of the halting problem as a stimulus to advance his programming methodology. He called himself a mathematical engineer, he called himself a software engineer, and only later would call himself a computer scientist for other reasons. So the mathematical engineer is himself a scientist, while we have the Minskian kind of computer scientist seeking universal claims, wanting computer science to be a universal science. We have Dijkstra pursuing specific achievements in a very mathematical, rigorous manner, trying to construct software for a specific product in a scientific, mathematically rigorous manner. And this is considered scientific, but of a very different kind than Minsky's. And today almost everybody I know in computer science is looking at the work of Dijkstra and looking at the work of others with Minskian spectacles. I could just as well take John McCarthy or Martin Davis or many other actors here. And I'll come back to that. So I think, well, I hope I have convinced you that the Turing machine is a boundary object, and it makes a lot of sense if you want to look at computer science as an academic discipline, and that's the role the Turing machine plays. But now I'm going to try to shed some doubt on that. Is the Turing machine actually a boundary object? Well, so far, if I just look at Minsky with his universal science, and I just look at Dijkstra, who actually takes engineering to be science, then I think I can say we're talking about boundary objects. But what if we look at other people who use models of computation in their daily work, at least for the case of Dave Parnas, a Canadian engineer? And what about, let's say, even a fourth kind of profile, a historian, Grattan Guinness, who was studying the effectiveness of mathematics in the exact sciences? Well, for him, science was actually engineering. I'm paraphrasing, and I'll come back to that. For Parnas, engineering, software engineering, had to become as prestigious as electronics engineering, and should be placed right next to computers, next to Minsky's computer science, like comparing apples to oranges. But on the ladder of prestige, it should go all the way up. That was Parnas. So one slide on Parnas. As a rule, software systems do not work well until they've been used and have failed repeatedly in real applications. So there's a lot of testing and debugging in Parnas's engineering, while you cannot say the same of, for example, Dijkstra with his mathematically rigorous approach, where you don't want to test or debug. I mean, in the ideal case, you can mathematically prove that your end product is correct. So, I think I'm being fair that if Parnas would engage with us in socio-technical terms, he would say that the Turing machine is not a boundary object because he would not embrace this neo-Russellian tenet that everything that's going on in physics, process-wise, can be captured with one and the same model of computation, because that's typically not what engineers do. And I've corresponded with him over the years. Then we have Grattan Guinness. Well, paraphrasing him, a scientific model merely approximates that part of reality which is being modeled. Mathematics in the exact sciences achieves a patchwork of approximations. Now we can agree or disagree with this position, but it's simply a fourth profile in the story, fourth way of looking at all of this. And again, I think I'm being very fair by adding this word not. There's no umbrella concept like the universal Turing machine, and everything can be reduced to that, and then we've got this universality. This is precisely the opposite of this universality claim. So the bigger picture, I think, would be that not for everybody it is the case that the Turing machine is a boundary object. In fact, it's for the computer scientist as a discipline that this makes sense. So now I want to become a bit more sophisticated in the sense of introducing the notion family resemblance. This is a family of 4 people, and their family resemblances, I would argue. I'm going to do this on the basis of 3 slides, starting with this one. If you look at the last line on the slide, in orange, the Turing machine is a boundary object according to those people whose names are printed in orange, while the Turing machine is not a boundary object according to the names in blue. That's my first slide. My second slide, in an attempt to convince you that we're dealing with a family resemblance, is that if you look at the last line on this slide, eschewing a science-engineering dichotomy is what Dijkstra and Grattan Guinness had in common. For Grattan Guinness, science is actually a patchwork, is engineering. And for Dijkstra, engineering is not patchwork, it's mathematically rigorous, it's science. Well, the people in blue would still embrace a dualism, if you like, between engineering and science. My third slide, look at the last line, eschewing infinite abstractions in your daily activities as a professional. That's precisely what Dijkstra and partners had in common. Because, and this is no surprise if, how should I put this, if you're trained in computer engineering, you want to build real things, you're not going to go for this infinitely long Turing machine tape. In your daily activities, at least, you will be embracing finite abstractions. So, to recapitulate, we have Minsky and Dijkstra. The Turing machine is a boundary object, and we can label this computer science, and many, many people fit in here. But the bigger picture is we have Grattan Guinness, partners, and probably even other profiles. And then I'm tempted to go to the family resemblance concept. The research questions which Edgar Schutbels and I are addressing are, of course, more nuanced than the question, what is computer science? They go actually like this. Our Turing machine practices only family resemblances, that is, they have nothing essential in common? Or is there a core in all Turing machine practices and the rest is different according to different goals, habits, and so on? Of course, the computer scientist would very much prefer a positive answer here and a negative answer there, and I'm coming back to that. So, I'm going to refine the question now. Well, in a sense, let me just emphasize that I just introduced the concept of family resemblance, but I want to be even a bit more nuanced. I'm going to take something from Hagemeyer's PhD dissertation from '79, which was not in the context of computer science, it was not connected to Turing machines, but he said something very interesting. I'm going to introduce that and then recast that to the present setting of computer science, and then I'm going to extrapolate that, and then we're going to talk about a permeability table, which is actually family resemblance explicated. So now I'm actually stepping away from a historical analysis. I'm doing this also with Edgar Schutbels, and I'm going to become a bit more Wittgensteinian as I go along. So, Hagemeyer said something very interesting. It is characteristic of technology that theoretical problems may disappear without the help of a theoretical solution. So if I recast that, in the present context, we get this. It is characteristic of computer programming that a theoretical problem may disappear practically, that is, without the help of Turing machine theory. Now, I've been educated in computer science, and as a PhD student in engineering, I had a co-supervisor who was like Minsky, and he said, no way. This Turing machine theory dictates the do's and don'ts of your work as an engineer. But I was already very much inspired by Dijkstra, and he would actually say precisely something like this. In fact, he would say it is characteristic of my programming methodology that the unsolvability of the halting problem disappears despite Turing machine theory's incapacity. And I mentioned in passing that this seems to be a bit Wittgensteinian on contradictions, because we have Dijkstra in his mathematically rigorous approach circumventing all those cases where you will encounter the unsolvability of the halting problem, and that's because he's always working with finite abstractions. Now, that's a crude statement based on what I learned from this morning, and we can skip this right now. I'm just trying to learn as I go along. But at any rate, Hagemeyer's statement is vindicated in retrospect by combining his statement and his work and then our knowledge about computer science, the history thereof. So that's Hagemeyer, but now we want to mutate or modify his statement many times by means of a permeability table, so that we actually get a long list of very specific statements. The first statement is actually Hagemeyer's original statement, but all the other statements are obtained by mutating the original one. And that long list of statements obtained in this way is actually family resemblance explicated in the context of computer science. So we have a permeability table with problems, solutions, theoretical, practical. This is some hand waving I'm doing here. You can fill this in many ways, and then you get a long list of statements. The first statement we already encountered. Theoretical problems may disappear without the help of theoretical solutions. That's one permeability case study, permeability between theory, Turing machine theory, and computer programming practice. But you can get a slightly different statement by modifying that, and we get practical problems may be solved without the help of theoretical solutions. So, we found a historical case study to check off statement A, because I referred to Dijkstra's methodology. Can we find a historical case study to show that this statement is true? Likewise, another permeability case study is statement C. Practical problems may be solved with the help of theoretical solutions. And we go on. Theoretical problems may give rise to new practical problems, and so on. It's a pretty long list. But this is family resemblance according to us, explicated in computer science. So, I'm going to take a selection of that long list and look at statement B. Practical problems may be solved without the help of theoretical solutions. Can we find a case study in the history of computer science? Yes, neural networks, for example, failed in the past due to excessive computations. This was a practical problem, and one did not need computability theoretic solutions to resolve this. The success came in the past, I don't know, 20 years, I guess, thanks to today's electronics, and we can refer to Moore's law to explain all of this. So we can check off statement B. Let's have a look at statement F. Theoretical solutions may fail in practice. Can we find an example? Yes, in computational complexity theory, where they also use Turing machines in a particular way, so there's a Turing machine practice in play. A theoretical optimal algorithm can fare far worse in practice than a suboptimal algorithm, because there's a discrepancy between the asymptotics used by the mathematicians and the actual instances used by the software engineering industry, and this is explained at length in my oral histories with Donald Knuth. So we can check off statement F as well. This particular permeability case study also holds. Then we go to statement G. Practical solutions are theoretically misunderstood. Okay, well, indeed, Dijkstra's methodology is misunderstood both today and in recent decades because everybody is looking at Dijkstra's work with Minskyan spectacles. So I often get this question, was he able to solve the halting problem? The answer is no. Dijkstra resorted to finite abstractions only. Therefore, the unsolvability of the halting problem is merely avoided. So I'm going to stop with the permeability table right there. I mean, I didn't go through every entry in that long list, but if you want to believe me in the sense that we will do it in the paper, we will, for every single statement, provide a historical case study to show that each statement is true. Then we can speak of a table which illustrates complete permeability. Complete in the sense that every specific statement holds at some point with regard to a particular practice. And now I'm going to provide an answer to the question, what is computer science? I'm going to say computer science is based on a conflation of complete permeability and something else. And that conflation is made by historical players, but also today. For example, I already alluded to the fact that many people look at everything with Minsky spectacles and misunderstand, for example, Dijkstra's work. And that's because they're conflating complete permeability, which is based on historical case studies, and then something else, which I'll explain in a moment. So, based on this permeability table and the long list and our knowledge about the history of computer science, we can at least conclude that history steers us towards this notion of complete permeability. And here's the claim. This is conflated with the Neo-Russellian tenet, because nowhere in that list, or to the best of my knowledge, nowhere in actual practices is this used, the Neo-Russellian tenet. It's just postulated in the textbooks. So I want to recapitulate that the Neo-Russellian tenet is a proclaimed isomorphism between processes running formally, if you like, and processes running in the real world. And this is basically the summary. This is the takeaway message. There's a conflation in play. And now I'm being very Wittgensteinian, not at all talking as a historian. This is nonsense, precisely due to the specific permeability in each case in the table. So once again, we're steering towards the conclusion that we have complete permeability, which does not make the physical and the formal exchangeable. To do that, you would have to have this Neo-Russellian tenet, but if you look carefully at each of these textbooks, it's just like going back to Russell's days, where he just postulates a couple of things. Let me just be brief and refer to logicism, and then there are contemporaries of Russell who clearly disagree with this. So we only have case-by-case permeabilities, and then our Wittgensteinian final move goes like this. Again, based on historical observations, there's complete permeability, but each permeability is different, and they do not add up to anything but a patchwork. So, I want to end with some future work. Ein Bild hielt uns gefangen. Well, what Minskian computer scientists assume with the Neo-Russellian tenet is, this is future work, the dog-rabbit gestalt switch. The causal seen as a manifestation of the formal seen as a causal entity, and I've published about a lot of this in a 2021 article in Computability. And in fact, there's a whole history of conflating these two realms, going back centuries. And then my final slide, I have here more or less the computer scientists engaging with me, if you like, is saying something like this. Look at the symbolic machine, it's working causally as a real machine. And look at the actual machine, it's a formal process leading from one state to the next. And then now in blue, I put on my Wittgensteinian hat and I say, but the causal and the formal are not the same. They are made to be looked at in computer science as dog-rabbit in between. Okay, so thank you very much for your attention.